So, and it's also been exposed to some environmental conditions. So all of these are factors that can affect, influence the response of different sensors during machining. So, like I said before, the amount of rust on the workpieces may alter what settings will be optimal for machining, as well as the hardness may change from being at the bottom of a stack, and then more hot forgings will come and sit on top of other forgings in a big bin. So these are all things that we're trying to kind of control, or not really, we can't control things like the hardness or the geometry, but we can change the settings which will improve the machining from these different variations. So like I mentioned before, the workpieces are forged, and from that process it goes in line from the forging. They will cool down to a temperature so that then they can be then put into a CNC machine. And that time period varies a lot. So it could be as little as 1 month, or sometimes the workpieces will sit out for 6 months or almost a year before they actually become machined products. And the end product for these workpieces are actually pipe joint or couplings for big oil pipes. So they will go in the middle, in between long pipes when they're drilling oil. And so the operations that need to be done on these workpieces before they can be given to the customers, as Dr. Shu mentioned, was outer diameter turning, inner diameter turning, facing cut, and then they are taken out of the CNC, rotated, and then they're drilled on the backside, and again turned on the outside and then turned on the inside. So if I open up the PowerPoint, is by using nice turning centers like this one, which have dual turrets that can come in and machine the outside and the inside simultaneously, and thus reducing the time in half. Instead of just turning the outside, bringing the tool back, pulling the upper turret, and then boring the inside, the CNCs are capable of doing multiple machinings at one time. So this greatly helps reduce the amount of cost, both in time for the labor as well as energy, if we're doing everything as much as we can in one time. And really the whole purpose of this, we can look at this simple manufacturing learning curve. You see here that the red line represents our break even, and the blue line is our learning curve. So the axis could be yield or dollars for the y-axis, and the x-axis is production, volume, or time. So by reducing the area, we can reach our break even, in which point that we are making profit. We're no longer spending money to make these parts. So that's one method of making more money, is to kind of tune your manufacturing process as quick as possible. And DOE, design of experiments, is a method to tune your operations, as well as we want to, once we pass the break-even point, we start to get in above the break-even, and we kind of know what's going on. And then we can also use DOE to create a larger gap between our break-even and our learning curve. And not just create a larger difference, but actually control that difference. So if we need to be lean, we can, hug or against the break-even, or try and go as far, and produce as much stuff as we can. So this is really the whole purpose of doing design of experiments, and particularly in manufacturing processes and operations. So what is design of experiments? Design of experiments is a method of obtaining and organizing knowledge so that it can be used to improve operations in the most efficient manner possible. And this was taken from reliability improvement with design of experiments. Design of experiments, a little history, has been going on for a long time. It started in England by a person called Sir Ronald A. Fisher, and he was using it to optimize agriculture, the output from plants, so that we could feed a lot of people. And he's the one who kind of started his own notes and wrote the first book, you could say. And then from then, it's been picked up by other fields, not just manufacturing and agriculture. Also in psychology they use design of experiments. And also not just in the manufacturing phase of engineering, but also in the design phase of engineering. You can analyze different factors to see which will influence the outcome the most. So Dr. Taguchi was the one who really pioneered design of experiments in manufacturing. And for design of experiments, it's an exploratory data analysis. So it follows this trend of first we need to identify our problem, collect our data, analyze the data, model it, and then arrive at some conclusion from our data. And below that, on the slide, we have kind of a block model of what's going on in design of experiments. So we see our kind of black box is the CNC turning process. We can think of it as we really don't know what's going on in the inside, but we do know what we are putting into it. And those things that we are putting into it are the spindle speed and the feed rate, as well as other things could be included like depths of cut, how much coolant is flowing, maybe you're only using 50% of the coolant. And then, so these are controlled inputs. Other things that I was talking about, like the hardness, the amount of rust, those are considered uncontrolled inputs. They're cofactors, and we have no control over them, but we do recognize their existence. And the output is kind of up to you. What are you trying to optimize? The output could be energy consumption, maybe the surface roughness, so you want to achieve as fast as machining while still maintaining a nice finish for your customer. Accelerations, acoustics picked up by the microphone, and things like that. So the basic steps to DOE, as I said before, is first recognizing and state the problem. So for General Dynamics, their problem can kind of be summarized as they want to be more competitive with other defense contractors. So they want to invest money into research and development to figure out how they can upgrade their CNC machines to kind of produce parts faster, which will save time, and use the least amount of energy consumption, which will save money, as well as prolong the tool life. So those are three things that we are studying for General Dynamics. The power consumption, the tool life, and the amount of cost to produce these parts. So recognizing the problem, we see that it's, we want to make it fast, we want to use as little energy as possible, and we want to keep that tool alive for as long as possible, and also not let the tool break while it's doing a machining, while it's actually machining, because if the tool breaks in the middle of the cut, it'll ruin the surface finish, and that just adds more money to having to rework the piece or even scrap the piece entirely.
There's a safety factor that tells you when, let's say if there's something breaks in?
That's what the point of our experiment is we're trying to categorize how can we tell with the microphone or a power meter when the tool is going to break. So if we can tell the operator, hey, the tool is going to break on your next pass, you've got this probability of it breaking, then he can stop the machine and change the tool before the failure actually happens. And so, looking into things like the microphone is very important because that's really what the machinists in the factory are relying on to understand if there's chatter occurring or if there's tool wear. And if they hear, they listen for certain signals to let them to know to change our overrides. Okay? And also in the factory, another problem is that the General Dynamics. Can you guys hear me all right? Yeah. Okay. So, as I said before, another uncontrolled factor is the machinist himself standing at the machine. Some machinists may prefer to, do things a bit slower and go at, 80% of the set G code. In that way they will preserve their tool for a little bit longer. But it takes them more time to get through a batch. And I wish I had one here that we could show. But I know you guys have seen these workpieces outside in the back on those crates. And you can kind of imagine a pyramid on that crate is equal to one batch. And you'll see how long it takes us just to cut 5 inches of material. If if one machinist is doing 80% of the feed rate and 80% of the spindle speed, it's going to take him a lot longer than say another machinist who is doing 120% and 120%. He's going to get done faster, but he's going to wear out a lot more tools. And so for General Dynamics, what we're providing them is kind of like where that optimal point is between these 2 points. And we've discovered that it's more of a region that you can be in where you're prolonging the tool life while also maintaining productivity. So trying to kind of give them a standard, and also they get like feedback on what does work and what's saving the most money. So after you it's all been kind of introductory about the project and the kind of experiment.
Export work rate because this red line in General Dynamics, they have hundreds of the same machine in red line in Pennsylvania. So our result, once we test our result, by the optimal condition, they will implement the same cutting condition in the red line. So the hundreds of machines, the same machine, they will use the optimal settings, which can save their cost. No matter it's human labor cost, or cutting tool cost, etc., or energy cost, power consumption cost, adding all together. So every part will be added together, and the summation of the cost will be minimum. This is the overall objective. So at this time, it's still offline. But next time, next phase, we are going to do the open, the online control, so adaptive control. So as the tool wear out, the tool condition, the cutting condition will be changed continuously. So we will use visual control algorithm, adaptive control, or robust control, all the different theory you can learn from the class. We will implement that in the machine tool. So the two nodes that Manny just showed you previously, the spindle speed override and feed rate override will be hooked up with the computer. So computer algorithm will calculate the control algorithm and update the feed rate or update the spindle speed will send to the machine tool directly. So these are hook up the entire loop, the feedback loop.
That's good. So yes, like Dr. Shi said, the General Dynamics has tons of these machines, and it's more feasible for them to put research money into upgrading the machines instead of going out and just scrapping all of their machines and buying brand new, maybe Siemens, 2012 machines. So these machines are very good. They're very big. They're very stiff. So they work well for turning these big steel parts. So we need to choose the factors and their levels. That's the next step in the DOE. Now for us, we have 4 main factors. The spindle speed, the revolutions per minute at which the workpiece is turning, the feed rate, how fast the tool is fed through the material, and the depth of cut of the outer diameter, and the depth of cut of the inner diameter, all going on at the same time. So there are 4 factors. But for our class, we're only going to focus on the feed rate and the spindle speed to show you how DOE works. Okay? So for us, our factors are going to be feed rate and spindle speed. Okay? Now after we choose our factors, let me talk about the levels. So if we set it at 100%, General Dynamics has been machining for a long time, so they kind of know what a good starting point is. And so we'll take that as our center point for our experiment, and we'll explore the area around their setting and see, is there something better than what they're currently using? And what they're currently using right now is 350 RPMs to turn the workpiece and a feed rate of 0.02 inches per revolution.
And what is the
The depth of cut? Right now the depth of cut is 0.16 inches radius. So they totally take off about 0.32 inches off the diameter in one pass from just the outside and the inside. So if you multiply that times 2, that's they're bringing it down. So there's a lot of material removing, and this is a roughing pass. So the depths of cuts are greater, the speeds are faster, and the feeds are faster, so they can remove as much material during the roughing cut. And it's during the finishing pass, which will take place in another machine, that they'll do slower and slower speeds, a lower depth of cut to get a nice mirror image on their final product to the customer.
That's 100%. These 6 those are 100%.
I'm sorry?
100%. Is that what you like?
Yes. Yeah, so our 100% for our feed rate is set at 0.02 inches per revolution, and 100% is set at 350 RPM. So, we'll drop down the CNC to 80 and do combinations. We'll do 100 with 80, 80 with 80. And so all of this will be taught to you guys through DOE, how to create and know which factors to use. But really DOE is about using your experience. So you can apply this to anything. You've got your own levels, and you can see just how your process is working, really. So next is step 3 in selecting our response variables.
We need to ask their background though, if they have any manufacturing background.
Okay, yeah. So I know if you've done through senior design, you must have some sort of experience in the machine shop. So I don't know, why don't we go around and get everybody's feel. So how do you feel about machining? Have you done machining? If so, what kind of projects?
Gas, internal cooling of gas turbine.
Internal?
Yeah, internal cooling of gas turbine.
Okay. So the manufacturing of the gas turbines?
Yeah, the blade, there's cooling hole in the blade, so we will try to find it. And when you're casting, you try to take off the model. So if you have some change to the performance, because the place is a little bit different about the cooling hole.
Okay.
Yeah.
So you need actual manufacturing? You do the actual machining? What kind of manufacturing process do you use?
What kind of process do you use?
What kind of manufacturing process do you use?
Casting?
Testing?
Yeah.
Okay.
Yeah. From casting.
And then you evaluate the different performance?
Yeah, because if you want to cast something, you have to take off the model. When you take off, if you take instead of that, it's different the folds. I mean, a little bit left or right, it will make the whole, the shape is a little bit different, the place is different, and it will be a big change of the cooling performance.
Okay.
Okay.
Did you do it in a company?
No.
Here in a senior design?
Yeah.
Okay.
Okay.
Very cool.
That's good. Who did you work with?
Dot Kapak.
Okay.
Provide? Okay.
Okay, well actually I work with product development.
Okay.
Yeah, when I was doing my masters in Finland.
Okay.
I work with Nokia Research Work and Wastella. They deal with ship engine.
Ship engines?
Ship engine.
Oh, wow.
So we used to do a kind of like product development.
Okay.
What
How to
kind of
develop.
material do you use?
Huh?
What kind of material?
Mostly steel.
Steel?
Steel.
Yeah,
Okay.
steel because it has to do with ship engine.
Okay.
Steel, alloy, and some other hard material that can survive corrosion because it has to do with sea.
Yes.
Okay.
So that's what we are working with.
What kind of process do you use? Casting,
Mostly
drilling,
drilling, milling, and
milling?
something like CNC.
Did you
Okay.
operate yourself?
Huh?
Did you operate yourself? Operate the machine yourself?
Yeah, most often I work with my professor, then I'm like doing the dirty job.
Okay.
Then he does like
And
the
he talk.
Yeah.
then he talks. Yeah. Yeah.
Okay.
Very good.
Very good.
Nice.
Okay.
Most of my research is in CFD, so I've had like very little or minimal experience. Even senior design here, we didn't machine anything. Most of it was handmade.
Okay.
So yeah.
My background is not too much. Also,
I'm sorry?
my background is not too much in materials. I worked quite ago, like on some kind of composite manufacturing a little bit, but it was mostly like baking, bagging, and all this kind of stuff, working with resins and that kind of materials. I'm not like I didn't have too much knowledge of those
already ready for the test?
Well, in this moment I'm working with Dr. Kepat so my background in this moment is like a turbine cooling. So it's pretty good to have the background from the manufacturing point of view because like it's related all the decisions that are being made when you're working say cooling stuff or on design. It's gonna have like an impact on the manufacturing. So if I have like a more knowledge in the manufacturing, it will be important because it will help to see the decisions we are making on the design point of view, what are going to be the consequences.
Yes. That's good. That's good. Yeah.
Mostly I've done hand turning or turning on the turret bench lathe we have here with plastics and stuff to make standoffs. Designed molds and other such things to be machined elsewhere, but least considerations for it, especially we handle a lot of water jetting. And we have to farm out. We have to farm out because we don't have one on campus. But that a lot of pouring and other composites manufacturing, which you usually try and do it so you don't have to machine it when you're done.
Okay. How much do you know about the NC program?
CNC.
Yeah, CNC program.
I used to write my own code in G line by line.
Okay, well that's what we
That's
do.
what we
here.
do.
Yeah, we call it fat fingering, where you actually have to type it in. There's no. This machine is old.
I had to teach myself that in high school because our little classroom CNC did not actually have any conversion software, so it was trial and error with a 3-axis CNC mill that just. I wrote something and then I screwed up a dimension, but it still worked.
Okay. At least it wasn't a crash.
I was the only one who could use it.
Hello. Yeah, I don't have too much experience about
You know everything.
but trying to learn about manufacturing. So that's one of the reasons I'm taking the class. So just to build up my knowledge. That's
It's good to have you here.
thank you.
Okay.
Thank you.
Okay.
Great. So yeah.
The background.
Yeah, so that's cool that you guys all have very, very different backgrounds. I heard composites, castings, also some turning as well. But I'm sure if you go to Google Scholar and you type in whatever it is that your background is in, castings or composite, and you follow that with the word design of experiments, tons of papers will pop up on this. So it's very used in all types of manufacturing processes, not just ours, and also through design phases as well. So I talked about our factors and our levels, our response variables for this CNC turning, and then it's about choosing your experimental design. So different types of experimental designs could include full factorial, where you're exploring, and this is better represented graphically. So, Okay. So after we choose our experimental design, and for this experiment we're doing a full factorial. So what that means is if we put our 350 and our 0.02 right in the middle, and we only have two high and low, 20% below 350 and 20% above 350, we see that we'll get 4 points, or 4 different combinations around our starting point. And so the formula for determining how many experiments will be done in your full factorial is 2 to the n. So where 2 represents 2 levels, a low and a high, and n is the number of factors. So for us we have two factors are speed and feed, and at two different levels, 80% and 120%. So that turns out to be 4 experiments plus the starting point to see kind of where we're starting at, where the responses are starting at. And the other designs include half fraction, which would only be, designing this cube and only picking 2 of the corners, 2 of the other corners. And then there's designs by Dr. Taguchi, and we won't be talking about that in this class. Not that we don't like him or anything, just that it's just out of the scope of our class, and it's not what we're using in our research. But the benefit of using factorial over maybe, the standard guess and check is that you will learn more about your process by using DOE than just by randomly selecting your conditions and seeing what the response is. So I'm going to kind of switch gears now that we know what experiment design we're going to use, and we're actually going to conduct the experiment. And in the next class, we're going to give you guys the data and have you guys do some analysis and develop some conclusions on the data that we gather. Okay? So in machining, I'm going to go ahead and skip down to our experiment setup here. Oh, I had a nice representation right here of our full factorial. You can see all the different tests. And what we're actually doing is we have this G code that we programmed, and we're changing some of the bolded numbers. Here you see S350 is bolded, so we'll change 350 RPMs to 80% and 120%. The F200, which represents the feed rate, that will also be changed in the CNC code, as well as the depth of cut, but we won't be changing that today. And so this is what the standard G code looks like. If you haven't ever seen any G code. So it usually begins with a line number, and then it's just like, just like BASIC or any other programming language. It's commands to the CNC on what to do. But G and M code is how CNC computers interpret what their commands are. Okay, so we have some commands, and different machines use different G codes. So it's very important for your machine to understand its own G and M codes. For our Okuma, it's FANUC control type, and we see that G14 will select the lower turret, and then we've got T0404, which will call certain tools, because you can see in this sort of CNC, we can put in many tools. We can do facing and turning and boring, all without even having to put a wrench in there to change the tool. The turret will pop up, rotate, and then it's ready to go for the next operation. And that can all be programmed within the G code. So that's pretty much it. Do you guys have any questions about G code? I know that's kind of, you don't need to know specifically what this certain command does, because it's different for every machine, but just understand that it's a programming language that gets interpreted by the machine. Okay, and so as I mentioned before, our responses are going to, for this experiment, so this is our entire, how our data is flown from all of the different sensors into our nice National Instruments PXI running LabVIEW real-time. So we have 6 different data acquisition cards, all going at, at variable rates. Our lowest sampling rate is at 10 Hertz, and at 10 Hertz we're collecting temperature data. The temperature using thermocouples, and this temperature includes the ID temperature near the tool and the OD temperature near the tool. We also have a microphone, as mentioned, and that's being recorded at 40 kilohertz. And we're also recording turning forces with the dynamometer at 20 kilohertz. And that's what the kind of gray block there is the dynamometer, and it's measuring forces in the X, the Y, and the Z direction. And all of these directions can be corresponded to the lathe coordinate system. The lathe feed direction will represent one axis. The lathe main turning force will represent another axis, and the feed will represent, and the radial will represent another axis of the machine. Okay, as well as accelerations. on the tool. So on the back of our tool, we have an accelerometer. Okay. So for your reference, I've included a diagram of the different forces, so that you know that the force of the X on the dynamometer is vertical in the page, and this kind of represents the main radial thrust force produced by the CNC. The force in the Y direction is horizontal to the page, and that's representing the feed force of the CNC. And the force in the Z direction is out of the plane, and that's traditionally called the main cutting force of the CNC. Also, the accelerometer turning diagram. And I also include pictures where you can see where it's actually mounted. So let's go back up to our experiment worksheet, and that's the next important part of doing the experiment. And before I go, I want to say that all of these sensors are all running at the same time, and we're collecting data simultaneously from all of the sensors, and it's a total of 21 signals ranging from 10 hertz to 800 kilohertz. So it's a lot of data. And next we have our experiment worksheet, and I'll pass it around so you guys can take a look at it. And so pretty much what this is just ensuring that we follow some sort of procedure and we don't make a mistake, because there's, we have to control the machine, control our data acquisition, just to make sure that we get as much data as possible and don't overlook any little piece of information. And we do things like check the condition of the thermocouple. Maybe the thermocouple broke in the previous pass. Make sure that we load new tools if that's the kind of study that we're doing. Make sure the CNC parameters are set. So people will, in our research lab, we initial the boxes that you have taken responsibility for that particular task in the overall experiment. So there's some other things that we record. We record which tool we've used. On the back side of the sheet, we see, we record which tool we've used, and we've been cataloging our different tools according to box, and then within the box, each tool will get its own letter, and then on top of that, there are multiple sides of these tools. If I take one out, you can see that the tool really has many edges, and this is like a tungsten carbide tool, so it's a lot harder than steel. So yeah, you take a look at it.
So it's used as a shaving to shave the part?
Yep, to remove the material. And before we go, we're going to do an experiment for you guys, so you can see actually us all collecting the data and everything. And so the tool has, for that one, it has 8 usable edges. And so that's important because, we can turn the tool over and use a new edge. And so we're just trying to keep track of that so we know which experiment corresponded to which edge. Again, we're measuring, taking a qualitative measure of the amount of rust. So on the worksheet we see that, whether it's a little rust or a lot of rust. And again, doing, measuring the geometry error. So we will actually go around and measure the different wall thicknesses to see how much the inner circle is offset from the outer circle. Because from the forging process, the inner circle, and with respect to the outer diameter, they're not going to be perfectly lined up. There's going to be some sort of variation, and so we also take that into account as well. So that's our pre-test offline data of our uncontrolled factors, and then offline test data of some factors will include how the surface quality of the workpiece. So we'll have a roughness meter that will probe along the edge, or probe along the surface of the workpiece, and let us know how nice the finish is. And General Dynamics has told us their appropriate finishes, so we make sure that we keep in tolerance with their finishes here.
So you have to keep track of each piece. You have to write it down.
Yes. Yeah. We write them down. We get as much data, take pictures, and then we put them outside to go back and get rusty again. So we measure the hardness on top of surface roughness, and the chip formation colors, as well as is the chip continuous or discontinuous. So there's a lot of both qualitative and quantitative measurements taken. Okay. So now I'm going to put the microphone down so we can actually begin this experiment. And, okay?
But these are parts that have actually been cleaned or shaved.
These right here?
And then they put them back out.
Yeah, we put them back outside. So after we do an experiment, we got a blue cart that luckily Abdullah has given us that we don't kill our bats or have to go out and recruit some football players to carry them out for us. But yeah, we put them outside. They'll get re-rusty, and then we'll turn them around and machine the rust again or drill the holes.
What do you guys use? You said you test hardness. How do you do that on? Is it in situ or is it?
Yeah, let me get that. Let's get that out.
Do you guys use Rockwell?
We're using lead hardness, and so there's a conversion chart that you can find online, which will let you know approximately, what the lead conversion is to Rockwell or Brindle hardness. But I'll get
It's in the other room.
No, I brought it down.
Oh, you did?
Yeah. Will you bring over the surface roughness meter? Nice, nifty little handheld hardness measuring device. It's spring-loaded and it's all very automatic. We just turn it on, and we'll come up to the workpiece, and we'll mark 3 points on the workpiece, every 120 degrees, and then we'll just so this workpiece is about 545 lead hardness. So very nice, very easy to use, very convenient.
About normal for these workpieces.
Yeah, this is about normal for these workpieces. So again, the purpose of DOE is to kind of get as much data as you can very quickly, because time is money. So if you can do a minimal amount of experiments to get a lot of data, then all the more data in that short time is very beneficial. Okay, so this is what we're using to test our hardness. It's by phase 2, and then here we have our nice phase 2 surface roughness tester. A little probe, which we keep it's very sensitive, so we keep it in the packaging until we actually go up to record it. We'll slide in there, and then we'll press, power it on, and then press start, and the probe will move about 2.5 millimeters, and while it's moving, it's vibrating and recording, the different, how much it's deflecting is what I meant to say. So, and that's what we're using to record our surface roughness, and we do comparisons with General Dynamics as well. It's a good question. Thank you for asking that.
I was just curious because I was like, I don't see a Rockwell tester over here.
Yeah, no, that one would be so big. We have a nice little.
Well, that, or if you had a magical tool that went on there that you could do Rockwell testing with.
That would be a good senior design project. Something that can
Talk to
fit
her.
into-
That would save a lot of time and money if you could actually have it as part of the manufacturing process.
Have it indexed to its own custom tool,
Yeah.
and even we were even talking about when I first started the project, making something that could go ahead and gauge the different change in wall thicknesses, because as the forging happens and it's punched, the wall thicknesses vary because the outer diameter and the inner diameter are not perfectly concentric. The holes are offset from each other. So we also measure that. We use calipers to do that. Okay? I guess I should go ahead and bring up the data acquisition program, because that's another major part of our experiments. And this is something that a few of us have been working on for over a year to develop this. Because again, collecting 21 sensor signals ranging from 10 hertz all the way up to 800 kilohertz is very challenging. It's a lot of data. Getting 800,000 data points within 1 second, and considering the test will go on for 60 seconds. So just running through the list, I'll quickly.
Sorry.
Go ahead.
Do you guys back up the data to an external text file or raw file as you do this, or?
We're using a TDMS file, which is for LabVIEW. Yeah, it's
We do back them up on our external hard drives.
yeah, we back it up on 3 different hard drives.
Yeah.
Well, no, it's just I've observed undergraduates before not recording their data in actual files. Just that looks good. That looks
Yep.
good. Never having any proof that
Oh yeah.
what they did was right.
Yeah, so yeah, like you said, we're backing up everything to a TDMS file and put that on multiple hard drives so we never lose any of our data.
Do you collect the raw data and the process at the same time, or do you just collect raw and then process it?
Process it later.
Right now we're doing offline, so we'll collect raw data and then go upstairs to our computers and then process it, do
So you just
filtering.
collect the voltages, you collect
The mechanical units.
Yeah.
Okay.
We're collecting actual mechanical units. So we're collecting, I think it's pascals for the microphone pressure, newtons for the forces. We're using G's for the acceleration and Fahrenheit for temperature.
But
So
do you actually take the machine data as well and keep it just as a secondary check? So you can collect the pascals, but you also take the voltage output from the transducer.
yeah, we have both files.
Okay,
We have one file called, it's unscaled. So unscaled data is, like you said, and it's either, the raw voltage reading, and then we'll keep that file backed up, and then we have another file which is called scaled TDMS, and that is where we actually have our mechanical units, and that's all nicely included into our LabVIEW program. And so that'll be something that we can show you too as well. Yeah, that's a good question, and that's also a checklist on here that we back it up. Backup test data onto the external hard drive is the last step before we walk out of the machine shop. So, yep, so we're ready to go. Let me just fill this out. The date is the 9th. The time is 5:30. Oh man, this is going quick.
Yeah.
Experimental names. I'm just going to put the class. And I've already gone through all this, and I've loaded the workpieces. We loaded the workpieces. We checked the thermocouples. The only thing I need to do is change the actual CNC code, which I wanted you guys to look at. And then we'll start the test. Okay? And then after we do the test, I'll show you guys more of the LabVIEW programming. So let's turn on our lights. Make sure all of our blocks are on here. So we have a lot of signal conditioners through our accelerometer, acoustic emission, our dynamometer, charge amplifier. So all of that's good. Operate with that one for last.
Yeah.
So, check the condition of the thermocouple. Check. Load and label the workpiece. Check. Load experiment tooling. Check. Record pre-test offline data. It's not really a little rust because it's pretty clean. But yeah, you get the gist of it. We'll go through and, every time we're down here, and we've got 2 notebooks full of all of our experiments. We've done, I would say, well over 100, maybe close to 200 machining experiments. And we're also working with the University of Florida, or not anymore,
Now it's University of
North Carolina in Charlotte.
Yeah.
Okay, so pre-test offline data. Now set the CNC programming variables. So for this test, we're doing the center point test. We're just going to machine at Red Lion settings. So we'll make sure that our spindle speed override is 100 and our feed rate is 100. And then we'll go into our CNC machine. Let's see, edit. DOE2SV3 is the name of our code. And then in here we'll make sure that our actual code is correct. That's what we want it to do. And we do this, we'll draw it out, making sure all the coordinate points are exactly where we want it to go. And here's what it actually looks like. After I'm done double checking it, I will pass it around so you guys can look at the CNC code. And also, we use Access, Microsoft Access, to make sure that when we print out our experiment worksheets, that we get reminders of what we're supposed to be at. So for this test, since we're not doing any ID, we're just going to do some OD turning. That cut depth is 0, so it's not going to move. Our cut depth for our OD is 0.12. And like I was mentioning before, where it's been bolded, we just go over those line numbers to make sure that we're actually at what we want. So we go through 520 is M42, that's good. G97S350. That's good. Let's see. 545. Oh, we got to change our depth of cut
Gonna hit low battery.
to 62100. Okay, so yeah, that's just a double check for us to make sure that we're doing everything. You know, we oh yeah, oblique the pause. Yes, I had an optional stop in here that I want to get rid of.
Delete line.
Yeah, right here.
Yeah.
Okay. And then we'll quit. So this is saving the file. Okay. We'll go to auto.
So these numbers, the one you saw in XA and GA, this is those numbers.
These numbers right here
Yeah.
are actually representing the coordinate system of the tool. So it's it's how far the tool is. Yeah, it's in its coordinates. These units are in inches. Make sure my light is on. Do you want to put the camera mounted in our camera holder?
I was thinking we do a different view for once. We already have that view 100 times. Do this one.
Okay, that's a good idea.
Yeah.
Close it. Key. All right, don't machine it. Let's do a simulation run, okay? So load the program. Key select. Deal to SV3. 3. Yep. And so an important part of you're going to do the CNC. I'll do the back.
Yeah.
So now we'll go ahead, make sure that we're at 100 and 100. David will put the key in, and we'll work together to start the data acquisition and do the machining. Can it hold there? Are you gonna?
Yeah,
Okay.
yeah, that's
So
good.
you keep your hand on the
Yeah.
just in case. So I'm going to start the data acquisition, and then when I give David the thumbs up that our data acquisition is going, we don't have any late loops from our producer-consumer architecture, then he will go ahead and start the machining, and we'll collect data. So, are you ready to go?
I'm ready.
I'm ready.
You turn the dyno sensor.
What's up?
You turn the dyno switch on.
So right now, David's got his hand, just in case, on the control on reset, which will stop the program, completely. The light's flashing. I know that the code has stopped running, stopping the data acquisition. And so when we have multiple partners down here doing the experiment, some people can be running the data acquisition, transferring it from the PXI to the host computer, and then backing that on the external hard drive. While maybe another experimenter, David, is writing down the qualitative measurements about the chips, and then we'll do the hardness testing and things like that. So as soon as our data acquisition, right now it's going through and scaling the data, and then we're going to transfer it to the host computer, which we can then look at.
Also show them the machine surface. Take a look at the machine surface. It's very smooth.
Yeah, it's nice and shiny.
Yeah, yeah.
Yeah,
So
look
that
at
has
the
a
machine
very good surface
Also, look at
finish.
the chips. We don't touch the chips; they're very hot. When they're nice and
Yeah, that
hazel like that, that's a good indication that a lot of the heat has transferred to the chips, and then the heat has not gone to the tool or to the workpiece. So those are beautiful chips. Again, blue ones are very nice as well. But if they came out, you can see there's some silver ones in there. Those would be indicative that a lot of the friction has affected the tool or the workpiece and has not gone to the chips. Read lots of papers.
Yeah.
So it's done the inside and the outside both, right?
What?
You did the inside and the outside, right?
We didn't do the inside.
Just only
today,
the outside.
Just the outside.
Inside the hammer. Very nice.
Looks nice, right?
Yeah, it's nice.
What's the second outer tool for?
The second outer tool?
Yeah.
That's a facing tool.
Okay.
Yeah. So that's another operation is they'll come in, they'll clean off the face. So you can see kind of that one where we went straight up, but you can see that even, even though we were going straight, there's still some rust on the face. So they might have to do a second pass on that.
And does this thing have an automatic chip cleaner?
Yeah.
Okay.
Yeah,
I was trying
so-
to figure out what the tracks were.
Yeah, so we would collect some chips, put them in a little baggie, write which test number, the date, and then run the chip
Run a
conveyor.
belt.
Nice. Cleanup is automated. Oh, right. Yeah. Really not good?